Hi, this is my demo 4. I'm going to be demoing on 4B and 4C. So 4B, I can translate between algebraic expressions, truth tables, and logic circuits. And 4C, I can define SOP and POS forms, both canonical and standard. So let's switch over here. So here is a given truth table. We have 3 inputs, A, B, and C, and an output of Q. And so the first, we're going to go from a truth table to an algebraic expression. So what we want to do is look at where Q equals 1. So we have 1 here, 1 here, 1 here, and 1 here. So 4 of them. So now we're just going to look at our inputs, and if there's a 0, it's being knotted, and if there is a 1, it is just going to be itself. So first one, where is 1? Right here. So we have not A, not B, and C. Next one right here, B is the only one with a 1, so that will be not A, B, not C. Okay, next one right here, A is the only one with a 1, so we'll do A, not B, not C. And then our last one, they all have 1s, so that's just going to be A and B and C. So those are our 4 expressions for each output where Q equals 1. And so now we want to build a SOP expression with that. And first, so when I say the sum, that means it's being ORed. And then when I say the product, that means it's being ANDed. So we're going to take the product of each one of these, and we're going to sum them together, which will be our SOP. So we have this first one, and then we're going to sum it together, so OR, and then we'll add our next one, B, C, OR, then our next one, OR, and then our last one. So this is a SOP expression. So we have our products here. So the product of A, B, and C, and then that is summed with the product of A, B, and C. And then so that's the kind of the process of it. So sum is when we're ORing. So this is this one or this one or this one or this one. And then the product, it's being ANDed, so each one of these are being ANDed to each other. So now we have our SOP expression, and now we want to go from this expression to a logic circuit. So I'll hop over to Logisim, and I already built the circuit for the sake of time, but I'll explain my process of how I wired it and why I did. So here's our expression. So obviously we have 3 inputs, so 1, 2, 3, A, B, and C. And then we have our output of Q. And we need 3 NOT gates, 1 for each input. And then we'll need 4 AND gates. So for this first AND gate, this is going to be our A, not B, not C. So for this one for this part right here, this is the one we're doing right here. So this is going to be A. So you can see right here, A is wired directly into this AND gate. And then our not B and our not C is also wired into it. So that takes care of that one. For this one, this is our not A and B and not C. So for that would be this one, where is it? This one right here. So not A, and B and not C. So you can see we have our B wired directly into it because it's just being ANDed, and then our not C and our not A being wired into it. So that takes care of that one. And then this is not A and B, or and not B and C. So that would be this one, this first one right here. So we should have our C wired directly into it, which we do, and then our not B and our not A wired into it. So that takes care of that one. And then the last one, A, B, and C. So we just take each of our inputs and wire them before the NOT gate directly into it. And you can see right here. Get that? And so then we take that, all four of those outputs, and we OR them. And that will give us our output of Q. And the reason we OR is because of this sum right here, the addition. So it's that or this one or this one or this one. So it's this, the output is either this or this or this or this. So that's why we put that OR gate there. And so now we'll go ahead and test it. So when A is 1, we'll get an output of 1. That is for this one right here. When B is 1, we'll get an output of 1. That is for this one right here. And then when C is 1, we get an output of 1. That is for this one right here. And then when they are all 1, we should also get an output of 1 for this one right here. And you can see that we do. So then let's test to make sure this is really working by, let's say we get 2, so at A and C, we should still get an output of 0 because nowhere in this equation do we have where it's A and not B and C. So we can see that our circuit is working. And that is kind of the process of going from a truth table to an algebraic expression to a circuit. And so you can go either direction with this. So then if you wanted to, you could take this circuit and kind of play with it and get your outputs and either make a truth table with it or make a algebraic expression with it. So you can kind of go any direction with it. So now that's my 7, or not 7, that is my 4B. Now we'll move on to 4C. So we'll start with SOP standard. And so SOP standard it's a Boolean expression where ANDed terms, which are called product terms, are ORed together. So an example of this would be y equals A and B, or not A and C. So these ANDed terms are being ORed together. So this ANDed term and this ANDed term are being ORed together. So that is an example for SOP standard. So then we'll go to SOP canonical. So this is where each product term, the min term, includes all input variables, each either complemented or uncomplemented. So it's sum, which is the OR, of all min terms where the output is 1. So an example of this, where we have 3 variables, A, B, and C, if the function is true for min terms 1, 4, and 6, our equation would be y equals m1 plus M4 plus M6, which would equal not A, not B, and C, or A, not B, not C, or A, B, not C. And so that's a SOP canonical. So now we'll move on to the product of sum, standard. So standard POS. So standard POS, it's a Boolean expression where ORed terms, which are called the sum terms, are ANDed together. So it's kind of flip-flop now. Before we were ANDing ORed, now where the ORed terms are ANDed together. So each sum term may include some or all variables. So an example of this would be y equals A or B, and we could do not A or C. So now we are ORing right here, A or B, and not A or C. So now we will do canonical POS. So for this, each sum term, which is the max term, includes all variables, either complemented or uncomplemented. And so it's a product and of all max terms where the output is 0. So an example of this, so we have 3 variables, A, B, and C. So if the function is false for rows 0, 2, and 5, our equation would be y equals M0 and M2 and M5. So those are being added together. I'll show that by doing that. Which equals, so that would be A or B or C and A or not B or C, and not A or B or not C. And so that is how a canonical POS works. And that is my demo for 4B and 4C.